And I want to thank the organizers for such a wonderful conference. Um, I'm going to talk about work that I've done with Enrico Herman, there's Victor Roybon, Mikkel Roof, and Mao Zhang on the double copy called loop orders. So what we're going to do is first a brief review of the double copy, which I assume most people know, but we should talk about it. And then I'll explain also about past difficulties with the double copy as you start pushing to very high loop orders. Generalized unitarity will be something that I'll have to say something about because it'll play an important role in the story. And the key point I want to talk about is unique integrands. The integrands are gauge invariant. It's just maybe in the past we didn't know that, but anyway, I'll explain how that works. And the step-by-step procedure to get a gauge invariant answer. And then that'll lead to the double copy to all orders. Okay, and in fact, many of the ideas that I'll be talking about here, they're very simple. They've been in the literature. It's just the organizing it and thinking about the problem in the right way and understanding what the consequences are. Okay, so first thing, well, okay, we're going to be using generalized unitarity. Almost everyone here knows it, but maybe a few don't. So this is the method the basic method we use to build the loop amplitudes, starting from tree amplitudes. It's a gauge invariant method. You take on-shell tree amplitudes and you construct these cuts, which then get assembled by some systematic procedure, which of course I won't describe here, into an integrand. And that integrand should be equivalent to what you get with the Feynman diagrams. And what we talk about generalized unitarity. You can think of it as a generalization of unitarity, where you're putting many legs on shell in different ways, and then using that information to assemble complete integrands. Okay, let me say a little bit about the duality between color and kinematics, which is, of course, the point of this talk, of how to do this to all loop orders. So I think most people here know it, so I'll be quick. And the idea is you take an amplitude. Now, first, let's talk about the tree amplitudes, and you put it into a form in terms of cubic diagrams. Let's say at 5 points, there would be 15 such cubic diagrams, and you have color factors, numerator factors, and then there's Feynman propagators. And the first thing is there's a relationship between color factors. That's the Jacobi identity. So here's the Jacobi identity in terms of these color factors of the diagrams. And the statement is, this is a proven statement at tree level, we can always find an arrangement so that the numerators satisfy the same algebra as the color factors. And the point of this is that you can do gravity. We take an endpoint tree amplitude, there's your QCD, and if you want to convert it to a gravity amplitude, you put it into this format so that the numerators satisfy the same Jacobi identity that the color factors do. And then you replace the color factor with the numerator factor. There's your double copy, there's 2 copies of the numerator, and lo and behold, you get you get gravity. Okay, and that's of course very cool. And of course, the key application of this is to loop level. At loop level, this is a conjecture that you can do this. So there's 2 parts to the conjecture. And one part is non-trivial, the other one is trivial. The non-trivial part is we can take a gauge theory and we can arrange it always so that any triplet of diagrams that satisfy the color Jacobi identity, you can find an arrangement that it satisfies the same Jacobi identity on the kinematic factors of these numerators. And of course, these kinematic factors are dot products of momenta, polarizations, there can be spinners, and so forth. And then the trivial part, which is easy to prove, is assuming that you have this Holden gauge theory, then it gives us a way of going between gauge theory and gravity. Just take the color factor, replace with a kinematic factor. Okay, and it basically says that the gravity loop integrands are very easy if you can find this duality between color and kinematics to hold in gauge theory. One thing is this remains a conjecture. That's not so good. But a much worse problem is at high loop orders, it can be very hard to find such numerators that satisfy this. So let's have a look. Can we find such integrands in terms of these cubic diagrams? A really good example is for loop n equals 4 super Yang-Mills, which has been used to then double copy into n equals 8 supergravity, study ultraviolet, have a lot of fun with that. And this works very well. Okay, here's one. Two loop 5-point identical helicity Yang-Mills. And the answer is yes, you can do it. But the expression has an oddly high power count. It's not a great representation. That's not so great. But there's a much worse problem. 5 loops, n equals 4 super Yang-Mills. And the answer there is no one has found one, despite considerable effort. And there is a way of getting the double copy, but I'll say a little bit about that. But that's a much harder proposition. And this problem, it's actually a very serious one. So in case you're wondering how come you haven't heard new progress on multi-loop supergravity and ultraviolet divergences and all that, okay, this is the reason, right? This causes a very serious problem. When you get to these very high loop orders, there's simply no other way to do it or no other known way that we can do these calculations. We have to have the double copy to make progress. Without that, you get stuck. So actually, here is a partial solution to the problem. This was used to make progress in that the 4.5 loop n equals 8 supergravity. We didn't have a double copy, but we found a patch that could be used to get the double copy without having the color kinematics duality work. Okay, and there's an interesting set of formulas that you can use. So what you do is you start with some Yang-Mills, super Yang-Mills, or some gauge theory integrand, and you just naively double copy it. That is the wrong answer for supergravity because it doesn't those numerators don't satisfy the correct relations. You don't get something sensible. So it's wrong. But it turns out it's only somewhat wrong. So you start patching it. And there's a set of formulas that you can find called BCJ discrepancy functions. It's basically the triplet of numerators doesn't satisfy the right Jacobi identity. It's broken. But then you take that broken function, this thing that's broken, and you can use it to find patching functions, like contact terms that are missing. You can systematically work this out. And this worked well enough, at least, to get the n equals 8 supergravity in 5 loops. It basically you can do the double copy without having this representation. And okay, there's the good thing. We actually used it in a highly non-trivial case, and made some progress. The bad was it gets harder to use as the loop level goes up, or the supersymmetry is reduced. So it's a formula that becomes harder and harder to use, an idea that's harder and harder to use. And I guess the ugly part is if you would actually see some of those formulas, the more complicated cases, you wouldn't be so impressed. It doesn't scale so well. We need a better solution. Okay, let's have a look at how the double copy works. Well, let's go back to tree level. So the first thing is there's many interesting supergravity theories that are very simple double copies. You just take the numerator, the n equals 4 super Yang-Mills, n equals 4 super Yang-Mills, and you double copy, you get n equals 8 supergravity, and n equals 5 supergravities, n equals 4 super Yang-Mills times n equals 1. Yes, it's true. 4 plus 1 equals 5, and so forth. It works that easily. Okay, but you may notice a problem. Let's say you're interested in Einstein gravity, which you might be interested if you're interested in our universe, not some supersymmetric version of it. And the problem is the double copy has extra states. Take a gluon times a gluon, you get a graviton. That's good, we like that. Antisymmetric tensor dilaton, unwanted states, right? So we need to get rid of these things. Okay, and at tree level, that's not really a problem because what happens is, let's say you put gravitons out here on the outside legs, then if you look at the action for gravity coupled to the antisymmetric tensor and the dilaton, you'll see that, in fact, it decouples completely. But at loop level, you can't do that because the antisymmetric tensor and dilaton can circulate. You have to figure out how to get rid of it. And there is, in fact, a simple solution to this problem. What you do is you think about the unitarity method, how it works. And this is, in fact, how we apply it to gravitational waves. You need Einstein gravity. You have to remove the states. It's no problem at all, really. What you do is when you're doing your unitarity cuts to build the amplitudes, you just insert the physical state projector for the graviton, and you just get rid of the states you don't want. It's as simple as that. And then when you do the sewing of the trees, right, what happens, let's say there's a physical state projector on here, it's graviton, there'll be no unwanted states in these trees by the argument we said before. And this is, in fact, how we construct the integrands for gravitational waves. We just insert the projectors. You know, not a big deal. It's also been used, this idea was used earlier to reanalyze two-loop ultraviolet divergences of pure Einstein gravity to show, it should have said its divergence. The numerical value of the numerical value of the divergence is actually content-free. You might think a divergence means it diverges. That is actually not true. The place you should be looking is at the renormalization scale instead. Now, I'm sure some of you don't have no clue what I just said, but that we can discuss afterwards, because I certainly don't have the time to explain the subtlety. It's actually something very cool that has to do with evanescent operators and the way gravity renormalizes. But anyway, these ideas were used earlier in that. It's also, of course, the gravitational waves. There's other ways, other alternatives you can do. You can use ghosts to remove states you don't like. Okay. So what do we learn? Okay. So generalized cuts, you can do that at any loop order. At any loop order for the cuts, you can manifest the duality, no problem, with generalized cuts, just because it holds for trees. If it holds for trees, it'll hold for the cuts, because you just build your gravity amplitudes, gravity trees, and you just sew them into these cuts. And then we can also control the spectrum very easily. Okay, and then what you have to do, the non-trivial step, is what you have to do is you have to take these cuts and merge them into an integrand. So if you'd like to claim that the double copy works at L loops, all loops, then what you need is a way to go from this side to that side that's smooth, that's easy to use. Then you can make your declaration. That's where the title of the talk comes from. Okay? So the key to double copy to all loop orders is not to think about the double copy, how you do this in the integrand. You have to think about how to do much slicker cut merging. That's the key. Okay, so what's a slick solution? What does it have to look like? Well, the first thing is when you do the cut merging, you have a bunch of cuts, and you have to put it together into an integrand, and that integrand would then have all the correct cuts and all the channels and so forth. The first thing is no ansatz. So you shouldn't have large linear systems to solve. It has to be simple, like term by term is what you're looking for. You can't have uncontrolled growth, power counting growth, power counting growth in whatever gravity you construct. Because sometimes when you do the cut merging, you don't do it in a proper way. If you just did it kind of naively, you'd really make a mess of the ultraviolet properties. You don't want to do that. That would make your life miserable if you're studying ultraviolet properties. It has to be systematic. It has to hold in general. It has to be compatible with dimensional regularization. This is very important. If you do loops, you can't be in 4 dimensions. You have to be in D dimensions. A key feature we're looking for is the generalized cuts need a simple way to go into the integrands. And after you have the integrand or you're imposing cuts, it should be done in a simple way. So the question is, how do you do this? And the solution is actually kind of trivial. It takes a little while to think through why this actually works, but the solution is actually pretty trivial. The first thing, and this is the key, is you got to have a basis. A basis is very powerful because every term is unique if you can define a basis. So you need a concept of an integrand basis. Okay? And to make cuts work very easily, what you want to do is for the monomials that are in the numerators, you want to use what's called the inverse propagator basis for that. These 2 bases. One is the integrand, and one is the monomials that are in the numerator. And this is all, you could say, fairly simple. And sometimes simple ideas can have profound consequences. Can really make your life much easier. Okay, so let's see how this works. So the first thing we have to do is label things. And usually what happens when people start thinking about a basis and they think about labels, at that point they're confused because what happens at loop level is there's no canonical way to assign labels that are consistent across all diagrams. If you look at the planar case, only the planar case, we know exactly how to do that. There's dual variables, dual momentum variables, and that's been used very effectively by Nima and friends. Like all loop n equals 4 super Yang Mills planar integrand. But the non-planar case, that resisted this idea of defining some kind of global variables. There doesn't seem to be any reasonable way to do that, some canonical, natural way to do it. So, of course, our solution is to ignore this point. We're not, we would like to have some kind of globally defined labels across all different topologies, but if we can't do it, never mind. There's something much more important, which is the global integrand basis. We need to have a basis. Okay? And what this basis is can be arbitrary, but it has to be a basis. That's the key insight. Okay, and once you have a basis chosen, the basis will be arbitrary, but the integrand written in that basis will be unique. No matter how you calculate it, that basis, in that basis, you always get the same integrand. Well, the first thing to construct this basis is assign some labels as you like. You just, there's, okay, the external momental, let's leave those labels fixed. Internally, you just pick something. Okay, then the next thing you have to do is organize diagrams in terms of parents, daughters. Okay, so you take this diagram and you pinch it in all ways, so that gives you there's 4 daughters. You'll find them in here. You pinch, let's see, here's, this is a different labeling. You pinch that in all different ways. Remove one propagator, and then you write down all the independent ones. This is the set of independent ones. There's 6 of them. And then you can go on. You can take the daughter and the daughter. There's one more pinch you can do here. And then you get 3 of these bubble type diagrams. You can continue the process, but let's put this aside for a moment. Let's just put this aside. We'll return to this. Don't worry. Okay, so let's see how this works. So let's look at a 2-loop example. suppose I have a set of diagrams. Maybe I'm doing Feynman diagrams, so there's actually a diagram with a contact term here. And there's some numerators which might cancel a propagator. So I could find some terms that really look like this topology here, that the propagator cancels. But you might notice the labels are different, right? Like this one has the L1 down here, there it's like that. It's just labeled in some different way. But what I do is I collect all the contributions from these diagrams, and I'll show you a little bit more about how to do that. You collect all the contributions of this diagram topology, and you relabel them to what we call a representative diagram. So it's a representative label. So this one, if I pinch it, it goes straight in. This thing, I have to do some relabeling. So I have to do this relabeling to get this guy to go into that guy. Okay? And, the same, I can, repeat it again for these sets of diagrams. Okay? And one thing that's important, if you're wondering why let's say Feynman diagrams aren't gauge invariant, is because there's mixing between the diagrams at the integrand level. So if I work in one gauge or another gauge, I'm moving terms between these diagrams in some way, but they have different labels. So if they have different labels, they're never going to cancel. I'm never going to be able to cancel any kind of gauge dependence. I'm never going to have anything like a unique integrand. So I have to do a mapping into these I have to cancel propagators, and I have to collect all the daughter diagrams, and I have to relabel them to a uniform set of labels. And that way, you can say, maybe I'm going to have a basis. Now, one of the key things you need is a good set of monomials to make things work right. And so let's say we look at, let's say, monomials, let's say the dot products of loop momenta and external momenta. You just count up how many different monomials you have. Well, this would not be a very good way of doing it. There's 9 of them here. But this is not a good way of doing it. The reason is when you pose a unitarity cut, there's some relationship between these monomials that you have to solve. And you don't want to do that. So, of course, the answer is switch bases. Go to the inverse propagator basis. And those of you who know about integration know you will anyway go to the inverse propagator basis, because that's how you do integration by parts, and that's how all the computer programs for evaluating these integrals anyway, that's the way they anyway work. And so this inverse propagator basis, you'll find it in all the integration by parts programs. Suppose you have external vector polarizations, or you have spinors, it's all the same. Just consider this as what we call an irreducible scalar product. So these things, there's some extra ones that you don't cancel propagators, and you include this in the basis set. Okay, so it's just a set of objects that define a basis for the numerator. And the reason why you need that is because we're going to cancel propagators and to collect diagrams that belong together. That's the logic. Okay? And massive theories, it's very similar, up to one complication that I'm going to discuss below. Okay? This choice of ISPs, that's completely arbitrary. So it's some random basis. And there's also, you could say, some random sets of labels. You just label it however according to however you like. Okay. Now let's get to the global basis for the integrand. So the idea is we use inverse propagator basis for the monomials. Then those inverse propagators, you go ahead and cancel all that you can cancel. And here's the key idea. You think about this for a little while and you decide, every term is unique. Every term gets mapped to a unique location. Okay, by unique, it's not exactly unique because the basis is not unique. But once you choose a basis, then the mapping into that basis is unique. No matter what representation, no matter where you start from. And here's like one little example of what I mean. There's a starting term. It happens to there's the inverse propagator. It happens to cancel this term here. Okay, so I go ahead and I do the cancellation. But you may actually notice that L1 changed to an L2, but it just happened to be the daughter was labeled this way. So L1 and L2 got swapped. So I just cancel the propagator, then I do an appropriate relabeling. And by the way, relabelings are free. If you're ever going to integrate this thing, you anyway have to relabel. Yes, very important. Whatever you do, or the key point is this is a basis. It's not overcomplete. If it's overcomplete, you're in trouble because then there'd be ambiguities in where pieces go. Okay, so what's the key to all this? Cut terms are integrand terms. So there's a one-to-one correspondence between any term you find in the cut. So these are on-shell, and you're interested in off-shell answers, right? So the way it works is pretty simple. What you do is you take a cut, and if in the cut I find, let's say, this diagram, so the propagator didn't cancel, and there's only ISPs left in the numerator, okay, I read it off from here. And I collect that coefficient. Maybe I have to adjust combinatorics. Should only count terms once. Don't count them twice. Maybe there's a small adjustment with combinatorics, but I directly read it in one-to-one correspondence. And then I go to the, let's say, a piece that might look like this. I can fish it out of there. I collect it. This piece, I find this piece over here. Let's say this guy, I can fish it out of there. Okay, then I go to the next cut. I come over here and I say, oh, wait, I already calculated that. Don't double count. And I go to the next one. Oh, I already calculated. Don't double count. Oh, here's a new one. Count it. Right? So the slogan, map cut term equals map integrand term. You just do the mapping to the unique locations on the cut. That gives you the integrand. Okay, and you have to make sure that you have a spanning set of cuts, meaning that you have cuts that tell you every single term that can be in the amplitude as normal. Okay, so the relationship to previous work. So many of the ideas I spoke about here, it would sound familiar. You'd say, well, inverse propagator basis. Yeah, I do use that all the time when I do integration by parts. Okay, and there's also these mappings where you have daughters that are the same integral, but they're labeled differently, and then you want to map it. Well, you can find that in the integration by parts codes. Okay, multi-loop cut merging, of course, it's very old. And then, of course, also the idea of finding a basis, it's not the first time you heard it. So this is the work at the planar level using the dual variables. There's also work called prescriptive unitarity. That's something that actually works in 4 dimensions, but the idea of the basis is in there. What is new here is we're talking about D dimensions. So this is a basis valid in D dimensions. And the key, it solves the multi-loop double copy obstruction that we've had. Okay, and some examples, I'll show you a couple of these. So one of the gauge invariance and on-shell ward identities, it becomes manifest. So if you take an on-shell ward identity, remember, if you take the polarization, make it longitudinal, you should get 0. You can easily prove that at tree level, but at loop level, it may not be obvious. You think you're supposed to do the integrals. There's no need to do the integrals. It's gauge invariant in the integrand level before you integrate. Okay? And there's soft limits, so there's an example in our paper about that. And you can also manifest supersymmetry cancellations. As far as I know, at least for extended supersymmetry, there's no, well, actually I should say all supersymmetry because of various technical reasons. To manifest the the supersymmetry cancellation is completely unobvious at the integrand level. But you can do it using this because you map to unique locations. In fact, the supersymmetry cancellations become obvious. Maybe a comment about higher points. Those of you who know about one loop will know that a hexagon integral, let's say you try to go to higher points, you know that this can be reduced to boxes. So you know that if you try putting this in a basis and you're in 4 dimensions, then maybe there's some over-completeness because there's relations between these, so maybe you shouldn't consider these things as independent. Well, there's 2 options. One is you can work in D dimensions and then only go to 4 dimensions at the end. That will be a basis, and the basis will not be over-complete. The idea of completeness or over-completeness depends on the space that you're looking at. If you happen to go into 4 dimensions and you start using, let's say, spinor helicity, and you start using identities that are only valid in 4 dimensions, then in fact you should just apply those extra relations, and you can go ahead and do it that way. Yes, the fun with the massive case. So if you look at the massive case, there's a little spot of trouble, because you can encounter diagrams like this, which are not scaleless, and they have a 1/0 if you put this on shell. In the massless case, generally you can ignore anything like this because it's basically a 0 from here is stronger than the pole, if you think about it carefully. So in fact, all of this can be ignored for the massless case. For the massive case, it's more complicated. These pieces are ill-defined if you work at the level of the integrand. But one observation is the basis cleanly separates these ill-defined pieces. So these are terms that have no cuts. The terms that we're looking at have cuts, and those are uniquely determined in the basis. They don't mix with any of this. Okay? Now you say, okay, but you still have to figure out how to do it. Well, there actually is a very slick way that at least works at one loop. What you do is you use other information after integration. So these pieces you just forget about until after you've integrated everything. Once you've integrated everything, you know you have a set of functions that are missing, some simple functions, and then you think carefully about the infrared and ultraviolet ultraviolet divergences, and you can then use that to figure out the missing pieces. I should comment, there's an interesting connection to decoupling for m goes to infinity. That's an alternative way to think about the constraints that you need to figure out what the missing pieces are in the massive case. In any case, mostly we're interested in massless theories or classical limit of massive theories where none of these issues really matter. Okay. So let's say some consequences, unique integrands. What this means is that after you do this mapping, all gauges are equal. For example, Feynman gauge integrand is light cone gauge integrand. Those of you who are old enough to know what Mandelstam-Librand prescription is, or principal part prescription for one of these light cone poles. See, it's kind of amusing, all of the debate about how to deal with the singularity here. There's an extra singularity in light cone. At least for on-shell amplitudes, it's irrelevant because in any gauge, it's the same integrand. So you just take the light cone guy and you just reshuffle it, just using that mapping, and then you don't have to know what this Mandelstam-Librand prescription is. Okay, so if you're in the basis, then unitarity cuts work term by term. The cuts act trivially. We have our slogan, cut term equals integrand term. You can expose soft theorems, on-shell word identities, of course, the double copy. Now, here's some examples. So, of course, we want to check, does this thing work? So you go to some very high loop order. 4 loops is a good case. And you try to look around and see how do things work. Well, for example, here would be one example, which I'm going to show you in just a minute, is there's a Lagrangian for electromagnetism. And is the integrand gauge invariant as I promised. And in fact, we checked it, and I'll show you the check. Uh, let's say for loop n equals 8 supergravity in the classical limit, that was something we were interested in. We explicitly confirmed that once you do this mapping, the cuts are still correct. So the mapping doesn't ruin anything. It goes to a unique place and so forth. And also, this is exactly how we calculate for black hole scattering in Einstein's theory, order g to the fifth. This is exactly how we do it, and it's actually very nice because it removes garbage, repeated integrals. Like you can see the same integral with different labels. It puts it all in the same place, and it cleans things up. So that's actually pretty nice. Here's the gauge check at 4 loops, what it looks like. So I just showed you a little bit there. You can barely read it. These long things there, those are names of integrals in what's called fire notation. Anyway, the usual notation for integration by parts. They showed you a little bit. There's another 100 gigabytes of this stuff. This is the terms that depend on the gauge parameter. So we know what the answer is, 0. So you might say, okay, does your method give you 0 if you do the mapping of the integrand? You map the integrand to the unique, to the basis, this thing should be 0. Indeed, we did that, yes, it's 0. So it's like garbage removal. It removes, gauge garbage gets removed from the integrand. And now, okay, double copy to all loop orders after that story, it's trivial. Trivial because the double copy works for trees. Okay? And you can, if you need a projector thrown in, you put in a projector. And then you just apply the double copy, then you map the spanning cuts. Spanning cuts means the set of cuts needed to fully reconstruct the integrand. You map it to a basis, you read off the unique integrand, and you're good to go. And like I said, Einstein gravity, 5 p.m. Einstein gravity integrand. It's constructed this way. Okay, so this is a solution. It doesn't solve the problem of a color kinematics duality to high loop orders for Yang-Mills, like the Yang-Mills integrand. It doesn't solve that. It just sidesteps it. Okay? And in fact, the place this is going to be used is, of course, multi-loop supergravity, and hopefully the period of time when you didn't hear much about that is going to be over. And you can apply it any place is double copy. The story holds, double copy to all loop orders. This is funny. This nice plot with linking theories. These lines represent a single copy that overlaps. Now you can see lots of theories over here. And everything I spoke about applies. Okay, so the conclusions are multi-loop double copy on integrands. If you're working only on the integrand using color kinematics duality, that can be difficult. On the other hand, if you do it on the cuts, it's straightforward. We can control the spectrum using projectors. And the key was to construct an integrand basis, which I described in a little bit of detail. And I guess we can summarize the slogan. The slogan is an integrand term is a cut term. This basis makes manifest all sorts of nice properties, on-field word identities, power counting, gauge independence, soft properties become much clearer. Some of them are like trivially manifest. Okay, in the two applications, well, we use it to construct our gravitational wave integrands. It's a very slick way of doing it, and probably the place where it's more important because we really were stuck was it removes the bottleneck that stopped progress in multi-loop supergravity. Okay, thank you.
Thanks, V. So I wonder, with this new technology, what are the prospects now for 7-loop n equals 8? Do you think that's feasible?
Well, First, we should do 6. So 6, 6 is definitely feasible. Um, well, yeah, 6 is definitely feasible. So the Yang-Mills integrand. Oh, it's John Joseph somewhere. Oh, he ran away. But anyway, where he's asleep. Oh, there you are. Anyway, they've constructed a Yang-Mills 6-loop integrand. It was in a naughty form that you couldn't double copy it, but now you can. Of course, slightly unfortunately, you have to go back and take the cuts now. Had they known this from the beginning, then they would not have done it the way they did it. So they have an integrand that cannot be double copied. But anyway, I don't expect any technical obstruction, and I think 6 loops can be done. We're also much better at doing integrals now, as you very well know.
Yeah, thank you. It's fascinating work. Can I ask you, do you think is it possible now in retrospect using this technology to see what is the obstruction with the double copy at 5 loops without doing the whole calculation?
No, I don't think so, because what we did was we sidestepped the problem so completely we don't see it. So the problem, in a sense, it's not the double copy, it's the color kinematics. And since we don't, the solution doesn't deal with that color kinematics problem. So we're as confused about that question as we were before. I don't think we've gained any insight, because we just stepped around the problem. We didn't solve it.
Right, but for example, if you just look at piece of the answer, one of the cuts, which would contribute to the 5 loop, you would push it up and you can look at power counting that the term has. But I don't know, maybe that's not the same power counting as the would-be double copy.
I don't see a way. At least I haven't gotten any insight on understanding what went wrong in 5 loops, like what the underlying real problem is. And it's like I say, it's because we've completely sidestepped it.
Yeah, if you could say a little bit more about the soft limit. I mean, I can see that there's, of course, multiple terms at higher loops, right? There's the tree soft factor, and I can see that would be simplified. But what about the loop soft factors that multiply lower amplitudes?
So the way, okay, the basic way it works, if you could, maybe there's one cheat in what I said. So these are understanding the soft limits in the integrand. Now, I think you might believe pretty quickly that in the integrand, the idea of understanding the soft limits is not so complicated, because it's built out of the trees. The non-trivial part, which was, I just glossed over it because I didn't have any time to explain it, has to do with the interchange of limits of when you actually do the integral. That we don't have anything to say. So that what becomes manifest is the soft limits inside the integrand, and you see that exactly how it works. Yeah, that's right. Yes, that's correct. I was fast, but okay, no time to explain.
Hello. Thank you for that wonderful talk. This might be a naive question coming from an outsider from this specific field, but can you do the same construction for higher derivative theories of gravity like Horndeski, Sticky, and so on?
Yeah, well, the same basic idea of a integrand basis holds for any theory. It's universal in the sense, it's just sorting pieces into a unique place. So a higher derivative theory would just have higher power counting. The monomials would be worse. You have a much worse theory. But let's say checks of gauge invariance or checks of like Ward identities would be much, it's the same story.
Okay. As long as the dynamical field is tensorial. As
Um,
long as you can
as long as it
basically-
can be written in some quantum field theory way, like Feynman diagrams, and as long as the object is like an amplitude that's gauge invariant. I mean, there has to be some notion of, of gauge invariance or unique, some notion of uniqueness. Maybe you do something very strange. Well, anything off shell, you'd have trouble with this. These notions won't work right.
Okay, thank you.
So this is also a naive question. So there was this quasi-Chaffel-Hoff algebra history for constructing, gauge invariant numerators at tree level. Do you think this will continue?
So I couldn't quite hear your question.
No, so there is this quasi-Chaffel-Hoff algebra story of Henrik and collaborators to build like gauge invariant BCJ numerators at tree level. Do you think like this will continue? Be useful at loop level?
Well, what happens, no matter where you start, you wind up in the same place. And the place you wind up in is somewhere arbitrary because there's a choice of basis that's made. And that choice is an arbitrary choice. So you can start from the most beautiful place. You'll still wind up in the same place as if you were to start from the worst place possible. So, yeah, so I'm not sure how to, maybe I didn't understand the question. I mean, these things are gauge invariant in the sense you go to a unique place, right? So any gauge parameter, any choices you've made, let's say like you're using projectors with light cone denominators, all of that stuff disappears, right? So you go to a unique place, but you definitely don't go to a beautiful place unless you have an idea of a beautiful basis, which we didn't use.
Okay, so one last question.
Izzy, fantastic talk. So I would characterize the method of maximal cuts as using a basis, as creating an integrand basis, but definitely an overcomplete one, right? So
It's
I think one
overcomplete.
absolutely overcomplete, and one of the spectacular advantages of what you're doing here is you're really finding the minimal number of cuts you need to target an integrand, which is also useful when constructing gauge multi-loop integrand. I mean, the focus here was on constructing multi-loop gravity integrands, but this is just as useful, having this minimal basis
Yes.
when constructing gauge multi-loop integrands.
And I think I know what we need to do. We need to build a time machine, go back in time, tell ourselves, just do a little trickery like this. Then we would have been much better off. The difference between overcomplete basis and one that's an honest basis is of course enormous, because then you pick out one term at a time in the unitarity cuts. But unfortunately, we can't build a time machine
Yet.
Okay, so we're out of time. So let's thank Z again.